So today we're going to talk about Karnaugh Maps, and we use Karnaugh Maps to find the simplest way to build a logic function that is using the fewest logic gates, but it can be quite confusing the first time you see it. So I want to introduce Karnaugh Maps as just another way of writing down the truth table for any kind of Boolean function, and it's just a way in which groups the various rows of the truth table in a way that will allow great simplifications. So first let's think of a two-input function, and we can arrange the rows and columns. So a two-input function has 4 entries, and we can arrange them, rather than in a column, we can arrange them in an array, 2x2 array like here. So the 0, 0 entry is here. If the 0, 1 entry is here, the 1, 0 entry is there, the 1, 1 entry is here. So when we do it this way, things will go together in a way that will group the true outputs and the non-true outputs in a way that makes some sense. So here I have a particular function. It has 1 in the first column of the first row of the truth table, 1 in the second row, 0 in the third row, and a 0 in the fourth row of the standard truth table. But now if I enter the 1 from here, goes there, the 1 here goes here, this 0 goes here, this 0 goes there, and then I can say, okay, that is not A and not B, or not A and B, but I can factor out the not B part of there. It doesn't really matter. And so my two 1s end up both being in the top row, and therefore I can say, well, the top row goes with 0 on A or A bar. So rather than having this fairly complicated canonical form where I have 1 and 2, one or and 2 ands, I just write down the function itself. I can do it again. Here I take the function not A and B or A and B. Clearly B is in both. I can factor it out, so this function just is B. But if I arrange it in the Karnaugh map, the fact that both of these are B's has the two 1s lining up here, and the fact that the other two terms with B bars have 0s have them lining up there. I circle those two B's, and that's all I have, is the 1B coming out. So that works fine for 2 inputs. How can I go to a bigger set of inputs? Well, consider in this function, and I'm going to redo it, if I go around in an order like this, and then unroll that to go straight across like this, I get the result like this. But now notice my numbers don't go in byte order, in binary order. It's 0, 0 for A and B, 0, 1, but then not 1, 0, but 1, 1. I have to keep the B's together, the B's that were on this diagonal. As I unwrap it, it goes this way, and so it goes 0, 0, 0, 1, 1, 1, 1, 0. The second two rows are swapped from what you might expect, but that keeps those two on bits the same, and so I can still circle them to find that B. I know it's B because there's 1 in both of those columns. And now, having done that, I can add a third row, a 3-input function, or I can do the same as I did up here in the column to get 4 input functions. So if I want a function where I have A on in all, I'll see that they're all there, and so I can write down those terms, right? So here I have A, everything here has an A in it, that's what it means to be in this row, but I have not B and not C for this column, not B and C in this column, that's here, not B and C in this column, that's this term, and B and not C in that column. And so if I circle all those, I'm saying that I have all those terms, and from all those terms I can factor out A, and the rest just gives me 1. Another example of a set of bits, if I have a circle like, if I can circle a set of 4 like this, that means it doesn't matter what A is, and it doesn't matter what C is, but B is on. So if I look at those 3, here I have not A and B and C, that's this term, not A and B and not C, that's this term, A and B and C, that's this term, A and B and not C, that's this term, and out of all those I can factor the B out, and that's just what I get. If I combine these two, then I have A from this set and B from this set, and so I have this combination rather than these complicated terms. So now we'll go through the procedure for finding Karnaugh maps for 3 and 4 input Boolean functions. So first thing I do is I specify my function as a sum of many terms like so. So here's a specification of a function, 4 input function, and I've put, so each one of these terms has an A, B, C, and D in it, and each one of those represents a row of the truth table with a 1 in the output. And I have to place those 1s. For each one of these terms, I'm going to place a 1 up here. So that's shown here. So here I have not A and not B. That's this row. Combined with C and D. That's this column. So I put a 1 here. Second term, still not A and not B. But now I have C and not D. C and not D is this column. So I put a 1 there. Not A and B. That's this row. Not C is one of the first 2 columns, and D makes it here, so I put a 1. Then I have A and B. Not A and B is this row. Notice, again, the order goes here. Is not the binary order, but it's this flipped kind of order. So A and B is here. Not C and D is here. A and not B, the last 3 terms all have that. That's this row. I have not C and not D, C and D, and C and not D. So these 7 terms make these 7 ones in the Karnaugh map. So now once I've made the Karnaugh map, I have to group in groups of powers of 2. I start with 16. If I could circle everything, I would know the answer was always 1, but I don't have that. Then I go for groups of 8 in a rectangle, which will always be 2 by 4 in a 4 input Karnaugh map. I also don't have that. And then I go with groups of 4. And so when I go with my groupings, I have to be able to circle over from the back to the beginning, or from the top to the bottom. I can also think of that as repeating this row on the bottom, as I've shown here. And now I can draw a circle around this set of 4 inputs, and they all represent the fact that there is a C in the, because there's in these 2 columns, and there is a not B. So this all represents C and not B. And so that's shown here. So that's the first step. And then there aren't any other groups of 4. There are groups of 2. So here's one group of 2. This, by the way, represents what I found already. But this group of 2 represents, well, it has to have a B in it because of those 2. And then specifically, because it's in this column, both C, not C and D. So this is B and not C and D. Finally, there's one more group of 2 which overlaps with the group of 4 I had previously. And that's fine. I can overlap. It'll still give me this simplification. Because I'm requiring this in 2 sets, it's okay. It's in one set or the other, and that's fine. So here I know that because it's all within this row, I have A and not B. But then both these have in common that the D is turned off, so it's A and not B and not D. And so since I've now circled all the inputs that are 1 here, that's the complete statement of the function. And I've reduced from this long form for the Karnaugh map, for the canonical form, to this simple form from the Karnaugh map. And in fact, you can show that this is about as simple as it can get for Karnaugh maps.